So, the final step is we use our Hamiltonian formulation. So, step 7 we use alternative Hamiltonian formulation. So, it is perfect to stop at step number 6 and work the problem in the Lagrangian form, but we see that it is quite involved. So, we use the Hamiltonian formulation or introduce the Pontryagin H function. Okay. So, that is nothing but our Hamiltonian. So, our Hamiltonian, so let me call this as H, simply H. So, the H evaluated at optimal condition. So, whenever I use a star superscript, it is a optimal condition. So, H becomes V times x bar star u bar star t plus lambda bar star times my plant condition x bar star times u bar star times t, and then all I have to do is I am going to change our Lagrangian to the Hamiltonian description. So, notice that my Lagrangian can be written in the form of a Hamiltonian. This is also equal to H star at x bar star u bar star lambda star comma t plus, and then so notice that H contains the quantity inside the functional plus the right hand side of the plant condition, plus then we have the partial derivatives of the cost function partial x partial s partial x at start condition times x bar dot plus partial s partial t at start condition minus lambda bar x bar dot star. Okay. So, let me call this as our condition number f. Okay. And then again recall that s is our terminal cost function, right. And then let me quickly write down all my constraints from the Lagrangian form to the Hamiltonian form. So, my co-state constraints, let me call this as B prime, right. So, B prime is my control equation. So, the control equation, the control constraints in terms of Hamiltonian, becomes partial L partial u bar at star, which is partial H partial u bar at star set equal to 0, right. So, we see that u only appears in H. So, that change is quite simple. My Euler Lagrange, which we termed as A, now I term it as A prime. My EL equation is changed as follows. Notice that the original EL equation in terms of the Lagrangian was the following: minus d dt of partial L partial x bar dot set equal to 0. All I need to do is plug in L in the form of H, and we see that we get the following expression: partial H partial x at start condition plus second derivative of s with respect to x square at start condition x bar dot plus partial 2s partial x bar partial t at start condition minus then this quantity becomes partial total derivative of partial s partial x at start condition minus lambda bar star, okay, and this is set equal to 0. Now, this is after taking into account wherever whatever variables are appearing, right, and then since this quantity here circled quantity is the total time derivative, we use chain rule to make it a partial time derivative. So, this becomes the following. So, this quantity reduces to a minus of partial s partial x 2 and times x bar dot star, and then plus partial s second derivative of partial as partial x partial t minus lambda bar star dot. So, we have taken the time derivative. Notice I can cancel few terms, this term cancels with this one and this term cancels with this one, and we are left with a very simple equation, which is partial h partial x bar at the starred condition becomes minus lambda bar dot star. So, notice that now my Euler Lagrange equation has reduced to an extremely simple form, and finally, I complete the system by introducing my co-state equation and the boundary condition. So, my co-state equation, which was C prime, becomes my co-state equation, which was del L del lambda. So, originally it was the following. This is reduced to partial h partial lambda at starred condition is equal to lambda bar dot star. Okay. So, this is my co-state equation. We just plug in the value of lambda and see how it differentiates with respect to lambda. And finally, my boundary condition, which we denoted by E, is going to be changed to E prime. So, my general boundary condition, the natural boundary condition reduces to the following form. We see that this becomes h star. Well, I am directly taking all the partial derivatives in the natural boundary condition, which was initially written in terms of L times variation of T f plus partial s partial x at star minus lambda bar at star times delta x f. Okay. So, this is equal to 0 and I call this. So, now this is my E, condition number E. Okay. So, we have completed the description of the solution of this optimal control problem. We can again simplify our problems into various sub cases depending on whether our boundary points are fixed or variable. So, let me quickly describe some of the simplified cases. So, different cases of my boundary condition. The first case is very simple, fixed time point and fixed state variables. So, fixed final time. Notice that we are in our setup, we never change our initial reference point. So, whether it is the optimal curve, let us say this is my optimal curve, and whether it is the perturbed curve, it always starts with the same starting point, right. So, but let us say my first case is fixed final time. So, T f does not change and fixed final state, right, fixed final state. So, which means that even my final point does not change, and which means that our natural boundary condition is trivially satisfied, because delta T f is 0 and delta x f is 0, and what we get is, so delta T f is equal to delta x f, both variations are 0, and so the only conditions that we are going to get is the fixed point boundary conditions itself. So, x at t 0 is x 0 and x at t 1 is x 1, right. Okay. So, then the next condition that we can describe is, let us say it is fixed final time, but variable final state. So, which means that T f is 0, the variation in time is 0, but the variation in the final state variable is not. Okay. So, condition B is free final time and fixed final state, free final time, but fixed final state. So, what we have is delta x f is 0 and delta T f of course is not 0. So, this means that, so if delta T f is not 0, so so let me just quickly draw the diagram of this situation. So, I am talking about, let us say this is my time point t 0 and my time point t f, and my initial curve is, let us say the following, this is my x star, and x star changes in such a way that my final state does not change, but let us say my new perturbed quantity is T f plus delta T f. So, the final time changes, but the final state does not change. So, this is x star plus delta x. So, in that case delta T f is not 0, which means our natural boundary condition kicks in and we get the following setup constraint to be 0. We have h star plus partial s partial t, this is set equal to 0, which is the coefficient, this is the coefficient of delta T f, right. Okay. So, then what I have is C free final time and fixed final state. So, the other way round, fixed final state. So, let me quickly draw the diagram in this situation. Again we fix T 0, we fix T f, and we see that I get x star, and so I have free final time. So, my perturbed quantity is such, my perturbed state is such that my final time changes, but well free final time, but fixed, well free final, that has already been done. So, free final time. So, free final I would say state the other way round, but fixed final time. Okay. And I see that this is the scenario. So, I have x f and I have delta x f plus delta x f, right. Okay. So, in this scenario I have that delta x f is non-zero and my natural boundary condition kicks in and I get partial s partial x bar at star minus lambda bar star is equal to 0, and well that is it. So, we okay, so that is it. Well, even in case B we had one natural boundary condition and also we had the condition that x at T f is equal to x f. So, this was the fixed final state, right. So, this also needs to satisfy. Okay. And here we only have one condition, and then finally, we could have another situation where we have free final time and free final state in such a way that the final state moves along a particular curve. So, let us say I have free final time, but dependent free final state, and I see that this is also going to be x of t times and t here from t 0 to t f, but now my curve moves along in such a way that the perturbed curve moves along in such a way that it follows a curve. So, let us say this is x star plus delta x and my perturbed curve is theta, where my original my final point on the optimal curve and the perturbed curve lies, right. So, suppose so what I am saying is the following: suppose my final time point T f and the state variable x of T f are related such that x of t lies on theta of t, x of t lies on theta of t. So, what I see is the following: I see that x of T f is theta of T f and variation of x of at the final point will be, since it lies on the curve, is almost equal to theta dot, where the dot represents the derivative with respect to t at T f times delta T f, right. So, then my natural boundary condition will kick in and I am going to get a single expression H star plus partial S partial T at start condition plus partial S partial X minus lambda bar star, and this is evaluated at well, this is all evaluated at start condition times theta dot of T, and this is delta T f. And of course, the boundary condition for this boundary condition to be 0, which means that this underlying quantity will be 0, right. And finally, one last type of boundary condition that I have is free final state and free final time, and such that they are independently moving. So, free final time and independent free final state, right. So, free final time and independent free final state, if T f and x of T f not related, then I can write down. So, which means neither variation of time nor variation in the state curve are 0, and so my natural boundary condition will give me two sets of constraints. So, H star plus partial S partial T at the start condition is 0, and then the second from delta x f I get that partial S partial x minus lambda at start condition, this is also set equal to 0. So, this is directly from my natural boundary condition. Okay. So, these are all the steps that I had to mention. Let me quickly summarize all these steps, especially the steps via the Hamiltonian formulation, which is the easier out of the two methods. So, summary of the Pontryagin procedure or the Bolzá problem, which involves the cost function. Okay, so given my plant condition, so this is the statement of the problem. So, statement. Okay. So, given my plant condition x dot is equal to f, right, and my performance index, which is given by j equal to s, the cost function of x comma t, plus, well, this is at final time point, plus t 0 to t f of this integral comma t dt, and the boundary condition and the boundary conditions which are x at t 0 is x 0 and x at T f is equal to x f, which may or may not be free. Generally, we fix the initial boundary condition. We have to find the optimal control, which is given by u bar star. Okay. So, then the solution summary is as follows. Solution summary. Step 1, we find the Pontryagin H function, let me call this as H of x bar u bar lambda t, which is V of x bar u bar t plus lambda times, well, I continue to use lambda is lambda. So, lambda in general is a scalar function times f x bar u bar t. So, that is my Hamiltonian, and then the second step is we are going to minimize the Hamiltonian with respect to the control, minimize. Notice that we are writing the word minimize although we are taking the first derivative, and the reason being we are dealing with all about convex functions. We have seen that when functions are convex, our extremum is going to give us minimum. So, minimize h with respect to u by setting partial h partial u equal to 0, that is at the optimal condition, right. So, from here from this condition I am going to get the optimal value of u, which is a function of the other variables, the state variable lambda and t, right. And then in step 3 is we are going to write down our optimal Hamiltonian by substituting this optimal control variable, right. So, step 3 is from steps 1 and 2 find the optimal Hamiltonian H star, and we see that by substituting our u star. And then in step 4, once we have the optimal Hamiltonian, we set up our constraint equation. We have the state constraint, the state equation x bar dot star is equal to partial h partial lambda at star, and then my co-state equation, which is lambda bar star dot is equal to minus h partial x bar star, and then I have my I have my boundary condition, my initial condition x at t 0 is x 0, and my boundary condition which is given by h star plus partial s partial t at t f plus times delta t f plus partial s partial x minus lambda at start condition and evaluated at t f, this is set times delta x f, this is equal to 0. And finally, after solving all these equations, notice that these are n vector equations, but first order, and these are another n equations. So, we are solving 2 n plus 1 equations, the last one is this boundary condition. Okay. So, after the solution we can find we have found all the variables, the state and the co-state, and then we plug it back into our step 2. So, substitute x bar star lambda star into step 2 to get u star, which is what we were after or the optimal control, right. Okay. Well, one final point of discussion in this solution methodology is how about the sufficient condition. We have described the necessary condition for finding the optimal value. So, the sufficient condition is, we have seen to find the sufficient condition we have to look at the sign of the second variation, but the good news is that we are dealing with convex functions. So, the second variation is always going to be the Hessian of the second variation will always be positive definite. The only thing that we have to check is a relation very similar to the strengthened Legendre condition. So, the sufficient condition, as I just said, is we have to look at the sign of second variation of j from t 0 to t f of partial second derivative of h with respect to x delta x bar square plus partial h partial u bar square second derivative times delta u square plus 2 times partial h partial u partial x partial u partial variation of u times variation of x times dt. So, this is our second variation in general, and we can write it in the form of the Hessian matrix. So, integral from T0 to Tf times delta x delta u times the Hessian matrix, which is partial to partial x x and well partial x partial u. So, this is going to be the ith component, the jth component. So, this is ij. So, this is a second order tensor and times delta x delta u, right. So, I have written the above expression in a more compact notation, and all we need to make sure is that this Hessian matrix. So, let me call this as a matrix H. This is going to be positive definite, which is certainly the case. So, H, well, let me not say H, this is our matrix A. So, A is positive definite because our function H is convex, right. This is the general optimal control setup. We take convex functions, okay. And the only thing that we have to check is the following partial derivatives. Check the second partial derivative given by partial 2 partial 2h partial u2, this is equal to 0. So, all we need to do is check this partial derivative whether the sign is positive or not, and this is very similar, or this is very similar to our strengthened Legendre condition, right. Okay. So, we are now, let me just highlight the solution methodology by a few quick examples.